Hello, I'm Adam. I'm a PhD student in Michał Tomza group. Today I want to show you our recent result on the, in fact, new class of molecular systems that can be sensitive to the physics beyond the standard model. Okay, so my task has been made easier as we already had some introduction to the standard models and problems, but just to provide some numbers to somehow quantify this imbalance from the measurement of the cosmic microwave background and Big Bang nucleosynthesis, this how large was imbalance, we can say that for every one particle, there was 1 billion particle-antiparticle pairs. So just one particle versus 1 billion. So we are quite unique. It comes from this one particle. Okay, it was 1967 where Sakharov discovered that in order to have this imbalance, which in a standard model, it requires CP violation, which of course it is present in the standard model, the Kabibo-Kobayashi-Masakawa matrix, but it's not enough. We need more. So as a result of the CP violation, or rather T violation, because we assume that the CPT is a valid one, so then we can equivalently say that CP is equivalent to T violation. It can result in low energy observables, so exotic multipolar moments like electron dipole moment, nuclear magnetic quadrupole moment, or even in theory electric octupole moment. But for this talk, we'll focus on the electron EDM. Just how it works. So if we have our, for example, electron and it has dipole moment aligned or anti-aligned with respect to the spin, so of course parity will affect only dipole moment, time reversal symmetry only spin. So we know that it cannot happen. This symmetry must be violated because we cannot put 4 electrons on 1s orbital. Yeah, so that's the issue. So what's going on in the world of EDM measurement? We already heard today about the ytterbium fluoride, but 2 also very advanced experiments: thorium monoxide, the beam experiment, and already now in its 3rd generation. After we plan to improve some technicalities in their experiments to improve the sensitivity, and the hafnium fluoride, the current record of sensitivity. The new generation of GILA experiment will be a new molecule, the thorium fluoride cation. It will be much more sensitive, mostly because the scientific state will be the ground one. So there's no problem with decay from the excited state deep at delta 1, because thorium fluoride is a ground state. Okay, so what can be done? Because we know that in the standard model, the predicted EDM is 10 to the minus 35. So we still need to reach this accuracy. So what can we do is advanced quantum control. And for me, advanced quantum control means ultra-cold temperatures. So we know there's a lot of effort to laser cool molecules, but the problem with diatomic molecules for the EDM measurement is that usually electronic structure that supports laser cooling is not good for the EDM measurement because of the lack of omega doublets, which are quite important. Although, of course, there's many successes with the ytterbium fluoride, barium fluoride. So with laser coolable molecules, we need to start working with the 3-atomic, but we want still have fun with diatomics. So maybe let's focus on the creation, indirect methods of formation of ultra-cold molecules. So magnetoassociation, for example. So the associates, we already have ultra-cold atoms, and then using magnetic field, we can make ultra-cold molecule. Okay, we had a great talk by Matteo about the lithium chromium. We know this molecule is very light, so it won't be sensitive to the EDM. But 2 years ago, on the same conference, Matthew Fry gave a talk on the formation of ytterbium chromium molecules, a much heavier system. And after some time, we start thinking, okay, ytterbium is heavy. Maybe it will be sensitive to the EDM. Let's try to calculate something. And yeah, it turned out after many terabytes of RAM, many hours of computational time, we calculated something. But before that, we simulated also, we calculated the the potential energy curves for the ground state using the couplet cluster method. We also calculated the excited state, mostly because we will be interested to transfer our potentially Feshbach molecules to the ground or vibrational state to perform measurements. So we obtain quite accurate value of the potential energy curves, so equilibrium distance, potential well depth, rotational constant, electron spin rotation, and the lambda, which is spin-spin coupling parameter. And this is important that the ratio between lambda and B is larger than 1 because we can work in the Hund case A, so that would be crucial for us. So having this, we simply constructed the effective Hamiltonian, simulated the rotational spectra. So we can see that with the increasing omega quantum number, so projection of the total orbital electronic momentum, this omega doubling is smaller and smaller and increasing with increasing J. So the conclusion is that the best state to perform measurements in the future will be omega equal 3, J equal 3. So having those numbers, we calculated the splitting, which is equal to 15 megahertz. Okay, and quite standard, let's say, scheme of the levels of ytterbium chromium in that case molecule for the EDM measurement. So in the middle, so the gray dotted line, we have field-free case. So rotating molecule has this parity doublet. Then we turn on electric field. We have Stark effect. We have Zeeman effect. So blue dotted line, dashed line, and hopefully some CP violating signal. So based on the differential measurements for MJ plus and -1, we can, I believe, I hope, in 10 years, maybe, I don't know, measure something, hopefully. But okay, I forgot about saying something that for lambda I provide some range of values, because in principle, that was the hardest parameter to calculate accurately. It was super, super, super hard. Not EDM sensitivity, I think, but this parameter was super hard and was super important. Why? Let's look on this. So here we have dependence of the omega doubling splitting with respect to the value of the spin-spin parameter. So in principle, we can see the small change in the lambda can result in very large change in omega doubling. So it translates that, again, small change in the in lambda will affect drastically the electric field that is required to fully polarized molecule. Here in that case, we can see the E star, it means the 50% of polarization. So we finally concluded that the most probable value will be 0.16. So we need something like 100 volts to fully orient ytterbium chromium to fully control rotations. Okay, so now something from quantum chemistry. Because ytterbium chromium has 6 unpaired electrons, so we cannot use the method that Anastasia mentioned. So the method we use is the configuration interaction that is with the Dirac, of course, the relativistic version based on the many electron Dirac equation with unconstructed basis set and so-called generalized active space approach. So basically, it means that we can somehow split different part of orbitals into the valence, core valence, core shells, and study how different excitation from different active spaces will affect final value of our parameters. Of course, what the experimentalists measure is not EDM, is the total CP violating signal. For the paramagnetic system, the most important one is, of course, dipole moment of the electron, but also scalar, pseudo-scalar. There are also interactions like tensor, pseudo-tensor, but there are rather important in closed shell system. So we evaluated expectation value over these operators. Here we have Dirac gamma matrices, electron linear momentum. Here for the scalar, pseudo-scalar, we have also nuclear density at the position of nucleus. And the most important thing for us, for a very long time, the final value was 10 gigavolts. But like 5 days ago, I got the new correction, far more accurate, that the proper value for the effective electric field is almost 15 gigavolts. The hafnium is something like 23. But remember, we want to make some molecule ultra cold. So corresponding enhancement factors it will be 0.82 and 4 for the WS. And finally, having this, this effective electric field, we also studied how the dependence of the effective electric field as a function of the laboratory electric field. So we can see for the our mj equals 1, already we have for 100 volts, we already have full polarization. Here is the case if we assume that 10 gigavolts, but I believe we need to prepare new figures with 15 gigavolts, because the 15 gigavolts take into account triple excitations in our wave function expansion. So it is substantial improvement. Okay, I'm quite good on time. So I believe in this work we paved the way for a new class of molecules, because usually this is the molecules for all these precision measurements has 1 ampere or 2 ampere electrons. We have 6 ampere electrons. Of course, we cannot. We have our molecule is highly magnetic, so there is no this quasi-cancellation of the G factor like in thorium monoxide, where we have opposite signs from the spin and orbital momentum. But it was really nice work from the Nick Hatzler group, where they studied that somehow by using entanglement we can reduce the sensitivity to the electric field, but also with molecules of parity doublets and spins we can also find clock transitions also to reduce sensitivity to the external fields. We also performed some preliminary calculations for radium chromium, which basically can be equally, I mean, it can be also very somehow, let's say, easy to in the context of formation. I mean, easy, okay, much easier than, I believe, ytterbium silver or radium silver. And the effective electric field is much higher, it's 60 gigavolts. And for example, radium also, because of the nuclear deformation, will be also sensitive to the shift moment. So maybe at some point, it will be also nice to study radium chromium molecule in detail. So that will be all. Big thanks to our team. Alessio, here important remark, please cross your fingers, because we are waiting for the ERC evaluation for Alessio. If the answer will be yes, you got it, then we will start this experiment within the he will start, but with our support, okay? Yeah, so thanks to Michał and Marcin. And yeah, that's all from my side. Thank you.
Thanks a lot for this cool talk. Results? Questions?
Yeah, thank you for a nice talk. I'm curious, what did you add to make your results change by 30%? What was the
effective electric field? So all previous results were based on the single and double CI. Here we have triple and quadruple excitations.
Okay, wow. So that's very, I guess, yeah, with so many electrons, you'll be sensitive to correlation.
Yeah, so I mean, yeah, because the problem with Ethereum is that we have to correlate F shell, so we already have to correlate 14 electrons. So it's for this calculation, as I mentioned, we need like 5 terabytes, so at least more than 1 billion of determinants. So it was quite costly, but I hope it will be fruitful.
Thank you.
Other questions? I have one. What is the shift moment?
Okay, so this is also the TP violating effects in the hadronic sector. So basically, this is the result of the mismatch between the spin density of the nucleus and the charge density. So in that way, you can somehow an extra, and it's yeah, a mismatch between the spin density, and so we need to have the non-zero nuclear spin. Yeah.
Any further questions? If not, let's thank our speaker again.